start to write down the known and unknown quantities. And then we write down our relevant equations. So from last time in class, remember or recall the following two basic equations. We have position as a function of time, and then velocity as a function of time. Okay, the third kinematics equation, by the way, which I derived in class last time, it's not actually going to appear in this problem, so I'm not going to bother writing it down. Okay, now let me apply the equations here to the speeder. If we take a look at the position equation first, notice immediately that two things in it are zero. The initial position of the speeder and its acceleration. So then therefore this equation simplifies for the speeder to become the following. Position x is equal to the velocity of the speeder multiplied by time t. Once again, I got this by setting x naught and the acceleration a here of the speeder equal to 0. We just have this middle term here. So as long as there's no acceleration, you can kind of think of it in the following way. Distance equals speed times time. Notice that there are two unknowns, however, in the equation. The two unknowns are x and t. So of course this equation by itself is not enough to solve anything in the problem. In addition to that, notice that the velocity equation for the speeder is actually no help. The reason for that is because the acceleration of the speeder is 0. This term disappears, and you just have the constant velocity of 40 meters per second. So the velocity equation, when applied to the speeder here, mathematically doesn't help us. So in other words, this is basically as far as I can get by just looking at the speeder all by itself. So now we look at the police car. Okay, now the police car also, of course, begins at the origin when it's stopped at the light. Like so. That's how the problem is defined. The problem starts the instant that the speeder here passes by the police car. The police car, however, begins at rest. So the initial velocity of the police car, call it V0 PC for example, is equal to 0. And then the police car begins to accelerate to the right-hand side. We'll call that acceleration, APC. That's given to us as 5 meters per second squared. Okay, and then the police car eventually overtakes the speeder. That's down here like so. And when the police car overtakes the speeder, it's going to have the same final position x, even though we don't know what it is, as the speeder's value. Once again, that's how the problem is defined. The problem is defined with the police car here overtaking the speeder at that moment. So we don't know what that value of x is, nor, of course, do we know the time. But the time to go from here to here for the speeder is exactly the same as the time for the police car to go from here to here, because once again, that's how the problem is defined. So even though we don't know what that time is, it's the same for both options. And the last thing that we don't know about the police car is its final velocity. Can we just assume, by the way, that the final velocity of the police car is just 40 meters per second, the constant velocity of the speeder? Can we just assume that? No, absolutely not. In fact, as we see at the end of the problem, it's actually going to be a lot more than 40 meters per second, so we don't know what it is. So now for the police car, I have a simple diagram. I have my known and unknown quantities written down, and now I write down the equations for the police car. So when I write down the position equation for the police car, the first two terms here are equal to 0. The police car starts at the origin, and it starts at rest. So the position equation for the police car is like this. And then secondly, we have the velocity equation for the police car. So for the police car, the final velocity here, VPC, that's going to equal the initial velocity, which is 0, and then plus AT. So the velocity equation, when written down for the police car, looks like this. So, and now you'll notice here that there are 1, 2, 3 equations and 3 unknowns. The 3 unknowns are x, t, and the final velocity of the police car. So at this point, it's the algebra. So it is a system of 3 equations and 3 unknowns, but the 3 equations here are rather small and they're easy to work with. The easiest way to do the algebra is actually just to set the values of x here equal to each other. This is the x, remember, for the speeder. This is the x for the police car. But remember, they're the same thing. So let's just set the expressions equal to each other. So let me write the police car first like so. And that then equals for the speeder, the value of x for that, which from the formula above is this. Okay, now if you look at the expression here carefully, what is the only unknown? He has the time t so to solve for. However, be careful here. How many solutions for time are there? There's two. It's a quadratic. But what is one of the solutions for time here in this expression? Here?
It's 0 because they both start at the same point.
That's right. Notice that 0 equals 0 is one of the solutions for time. And he's exactly correct. It makes sense because, yeah, times 0, the position of the speeder, and the police car is the same. Frankly, we don't really care about that. However, we want to find the other time. So to do so, what I'm going to do here mathematically is just cancel out a t here from either side of the expression. And then solve for the remaining time by doing some cross multiplying. So move the 2 and the acceleration to the other side. And the time t then, therefore, works out to be this. So, and now I just plug in my numbers. So first of all, in the numerator, it's going to be 2 times 40 meters per second, which is 80. 80. And then divided by the acceleration of the police car, which was 5 meters per second squared. This gives us a time here of 16 seconds. Okay, and now that I know what that time is, then I can jump back to either, for example, here or here to find the final position of the two objects. It doesn't matter, by the way, which equation that I use here to find x. Doesn't matter. Yeah, because they're the same thing. So just to make it easy, let me go ahead and use this value here to find x. So x is equal to the velocity of the speeder multiplied by the time t. So this is equal to 40 meters per second multiplied by 16 seconds. So just doing the math here, 40 times 16. And that works out to be, it's kind of a big distance here. It's 640 meters, which is just over half a kilometer. And then lastly, finally now we can find the velocity of the police car as well when it overtakes the speeder by just using this expression here, because we now know everything on the right-hand side. So the final velocity of the police car is equal to its acceleration multiplied by the time t. So 5 meters per second squared times 16 seconds. So 5 times 16, and that works out to be 80 meters per second, which by the way is actually quite large. So the police car's final velocity at the end of the problem is considerably larger than that of the speeder. Okay? Okay, so that's how you approach a problem that is similar to this in WebAssign. In WebAssign, however, it's a slightly different situation, but you basically do the same thing. You diagram out essentially each object, and you then look for a way of linking them together. Okay. Nice problem to start with. Go ahead and do some erasing. Okay, when describing the basics of kinematics last time in class, I basically said the following. Velocity is the derivative of position with respect to time. Acceleration is the derivative of velocity with respect to time. The equations, of course, that describe all of this are the kinematics equations that we've seen thus far. Constant acceleration, position, velocity, and let me also write down the following for our situation here, that the accelerations that we're dealing with are constants. In order to understand what the derivative means in the context of motion, the easiest way to do this is actually to diagram out, to draw out in terms of the graphs, an individual problem. When we do, we're basically going to be graphing these functions. So for example, take a look at the acceleration when it's a constant as we're describing. If on a graph, we graphed the acceleration as a function of time for a constant value, what does the graph of a constant always look like? It's linear, but it has a slope of 0. It's horizontal. Then a little bit later on, however, if we graph out velocity as a function of time, we're graphing this equation. What kind of an equation is this? It's linear. So in other words, think of it as a line in the following sense. Think of it as y equals mx plus b, where the slope of the line is the acceleration, and the y-intercept is the initial velocity. A little bit later after that, however, is position as a function of time. The position as a function of time is a quadratic. And what type of graph or curve is always associated with a quadratic?
Parabola.
It's a parabola. That's correct. So to see exactly what the derivative means in the context of motion, let's graph out a problem. Okay, now at the end of this example, I'm going to ask for a volunteer. I'm going to ask for a volunteer to actually walk the problem. I'm throwing down the gauntlet to you right now. This problem was successfully walked by 2 volunteers in periods 2 and 4 respectively. You know, as you start to read through the problem and copy it down, notice that there are 2 discrete values of acceleration. There's an acceleration of negative 2 meters per second squared for the first 10 seconds. Yeah, that is a negative sign there, by the way, on the right-hand side of the second line. It's just how it shows up on my file there. And then there's an acceleration that's a different value for the remaining 5 seconds of the problem. So like in the last example, with this complicated example, you basically break it down into a series of parts. What we're actually going to do is just calculate first. Given the data that we have here in this problem, and think of it that way, given this data, what we're going to do is calculate the position and the velocity at the beginning and end of each time interval. Once I then have all that information, then I construct the graphs afterwards. So we basically just calculate first and then go from there. So calculations. Okay, let's just take a look at the first 10 seconds to begin. So from 0 to 10 seconds, and as we always do, let's assume that the car, in this case, just starts at the origin. So x1 is equal to 0. And then at the very beginning of the problem, it has an initial velocity of 10 meters per second. That's what's given in the first sentence. So v0 here is 10 meters per second to the right-hand side. It then undergoes the acceleration that's given of negative 2 meters per second squared, and it does so for a total amount of time here, t, of 10 seconds. So we're given all this data here to open the problem. And then we don't have to really do any algebra here or anything like that, but what we do have to do is take all these values that were given here about the motion over this 10-second time interval and plug them into the respective equations here to calculate the position and the velocity at the end of this time interval. Once I have those numbers, they'll then carry over into the remaining 5 seconds of the problem in just a few minutes. But the first thing that we do is just calculate. So calculate x and v. I'm going to do so by just plugging everything in. So for first of all, the position. For the position, it's going to be 0 plus 10 times 10 plus 1/2 times negative 2 times 10 squared. So let's see what we get. So 0 plus 10 times 10 plus 1/2 times negative 2 times 10 squared. And now here's what pops up on my calculator display. 0. The object started at the origin and ended up at the origin. So in terms of the motion, what must have happened to the object during this 10-second interval? It turned around and moved in the opposite direction. We're going to have to figure out later on in the problem when and where that happens. Before we do, however, of course, let's now go ahead and find this velocity v after 10 seconds. We'll do so by just plugging everything into the equation here. So it's 10 plus negative 2 times 10. So it's actually just 10 minus 20, or negative 10 meters per second. Notice the negative sign here for this velocity. This means that, yes, the object is moving in the opposite direction to what it was doing originally after 10 seconds. So somewhere in here, it must have turned around and moved in the opposite direction. We'll have to figure that out a little bit later. And now we get to the remaining 5 seconds of the problem. So now we're going to go from 10 to 15 seconds. And here, these numbers that I calculated now carry over into this interval. What I now have to think of is I have to think of this value here of x that I calculated as the initial position for the next time interval. It's equal to 0, but I'm not saying that arbitrarily. It's the same thing as the final value from previously. Similarly, this value here of the velocity from previously, now I have to think of that as the initial velocity over this time interval, like so. Okay, then the other data that's given here in the problem is that the acceleration is now positive 1 meter per second squared, and the time interval itself, t, is 5 seconds long. So I now just complete the calculations that I have to do here by taking those values there on the right-hand side of the board and plugging them in here respectively to find the position and velocity at the end of the problem. So now I find position and then velocity by just plugging in. So first of all, the position, using the data there on the right-hand side, we're going to have 0 plus negative 10 times 5 plus 1/2 times 1 times 5 squared. So let's say negative 10 times 5 plus 1/2 times 1 times 5 squared, and that comes out to be negative 37.5 meters. So the object ends up ultimately at the end of the problem 37.5 meters to the left-hand side of the origin. And then lastly is the final velocity. Just plug into the velocity equation. We're going to have here negative 10 plus 1 times 5. So it's actually negative 10 plus 5, which is negative 5 meters per second. We can start to picture the motion here if we look at these velocities. Notice that the object is still traveling to the left-hand side, but it's slowing down as it does from 10 to 5 meters per second. So far, we've calculated out everything. Now it comes to the graphs. I'm just going to sketch the graphs, that's perfectly fine, but you always sketch the graphs in a specific sequence. You always graph acceleration first, then velocity, and then position. So first of all, acceleration as a function of time. So here's the time axis, 10 seconds and 15 seconds like so. Here's the acceleration, meters per second squared. And now we take a look here at our data in the first 10 seconds. So in the first 10 seconds of the problem, the acceleration is a constant negative 2 meters per second squared. That's a horizontal line, like so. And then for the remaining 5 seconds of the problem, the acceleration is a constant 1 meter per second squared. So right here we'll say is a positive 1. And so then therefore for the remaining 5 seconds of the problem, our acceleration is the following. And now because you have sat in this school in various math classes over the last couple of years, you may be looking at this rather unusual, discontinuous, piecewise function and asking yourself the following question. Is this here an open point or a closed point? Is this here an open point or a closed point? And all of that stuff that they drill into your heads in math classes here at school. Well, what happens in this situation? Let me ask you this. Is it physically possible for a car to instantaneously, literally in no time at all, go from an acceleration of negative 2 to positive 1 meter per second squared? No, that's physically impossible. What instead happens? The following. Don't draw this. What actually happens is that over a short interval of time, as a smooth curved polynomial, the acceleration changes from negative 2 to positive 1 meter per second squared. There is a non-constant acceleration here for a short period of time. In introductory physics, you are always taught introductory physics in the following manner. you're always taught the idealized or simplified situations first. The reason for this is because typically they're easiest to handle mathematically. Once you understand how to deal with those simplified situations mathematically, then we add more complexity to the situation to approach physical reality. So for now, where we're ignoring non-constant accelerations, we're basically ignoring this detail. A little bit later on in Chapter 2, we'll learn how to deal with a non-constant acceleration, but for now, we're not going to worry about it. So then therefore, we just draw the graph exactly as I did a few minutes ago. Just quickly sketch. 15 time in seconds. So we have our acceleration of negative 2 meters per second squared once again for the first 10 seconds, and then positive 1 meter per second squared for the remaining 5 seconds. And we don't worry about points of discontinuity or open points or closed points or any of that nonsense that they drill into you in math class. Frankly, we don't care. And next is velocity as a function of time. By the way, all the math teachers here at school hate it. Okay, so now we have velocity as a function of time. Once again, we look at our time intervals here, from 0 to 10 seconds, and then from 10 to 15. So look at our data up here on the top board. So for the first 10 seconds, our velocity goes from positive 10 to negative 10 meters per second. So let's say that right here is positive 10. Let's say right here is negative 10. And we go from a velocity of 10 to negative 10 like so after 10 seconds. And now the question becomes the following. What connects these 2 points? What type of a graph? Linear. Because once again, we're graphing the velocity equation, which is linear, where the slope of the line is equal to the acceleration. It looks like this. So, and now here's where the derivative comes into play. On a velocity versus time graph, the slope of the tangent line is the acceleration. Think of the tangent line as the ruler's edge here. Notice that the slope of the ruler's edge over this 10-second time interval never changes. It's a constant value of negative 2 meters per second squared. This right here is the derivative of this. Notice, by the way, that this line crosses the time axis right here at this moment in time. This is the turnaround point. The reason for this, because right here at this instant, notice what the velocity is. It's 0. The velocity is going from a positive value to a negative value. So we have to figure out when this is, and then later on, where it is. But if you just look at the symmetry of my graph here, and I'm being careful to sketch it, obviously, pretty obviously, what is this time here on the time axis? That's 5 seconds. Here's how you show it. What we do is we set the velocity here equal to 0. And then we go, let me get something to point with, up to our velocity equation, which is right here. We set the v equal to 0. So, and now I just solve for time. So move the v naught to the other side, and then divide by the acceleration a. And then here's how the numbers work. This is negative and then 10 meters per second divided by negative 2 meters per second squared. 10 divided by 2, the negative signs cancels out. Gives you then a time here of 5 seconds. So that's how we explicitly show what that time is. And then lastly for this graph, we have the remaining 5 seconds of the problem. We go from negative 10 to negative 5 meters per second. So this right here is negative 10, let's say about here, it's negative 5, so I end up with a point right there. Okay, connecting the 2 points is once again a line. So there is a point of discontinuity here, but don't worry about it. Remember, we're ignoring the non-constant acceleration that occurs here over this short time interval, so just leave it as it is. And then once again, here's how the derivative works. Velocity versus time graph, slope of the tangent line is the acceleration. Notice that the slope of this line here never changes over that 5 seconds. It's a constant acceleration of 1 meter per second squared. So in other words, this graph is the derivative of this. And then guys in the back, we lastly get to the position as a function of time. This is usually the hardest part of this process. So time in seconds, position in meters, and 10 and 15 seconds once again, like so. And now we look at our position data. So up here on the top board, notice that we have the initial and final positions over the first 10 seconds as 0. They're the same thing. So from here to here. Now, what connects those 2 points? Well, we're graphing right here. Position is a function of time. It's quadratic. Once again, what type of a graph is associated with quadratic? It's a parabola. Which way does the parabola open? It opens downwards because notice that the quadratic term, the acceleration, is negative. Therefore, the parabola looks like this. Notice that we hit a vertex right here. It says label the vertices that appear on this graph. I'm starting to do so. The vertex here is at exactly 5 seconds. Here's how I know that. I know it once again on the derivative. On a position versus time graph, the slope of the tangent line, the slope of the ruler's edge, is the velocity. So right here at times t is equal to 0. I'm not going to draw it, but right here is the ruler's edge. What is the slope of the ruler's edge right there at t is equal to 0? It's 10 meters per second. And then the velocity goes from 10 meters per second to a velocity of what right here at 5 seconds? 0. Notice the slope of the ruler's edge here is equal to 0. So we go from 10 to 0. And then the velocity goes from 0 to negative 10 meters per second right here after 10 seconds. Notice the slope of the ruler's edge is a negative number. That's negative 10 meters per second right here. So this line is the derivative of this parabola. Okay, one thing as of yet, however, about the parabola that we don't know is where is the turnaround point? Where is the vertex? So in order to find the vertex, we look at our data. First of all, start right here with x naught equals 0. Our initial velocity, v naught, remember, was 10 meters per second. The acceleration was negative 2 meters per second squared. And now what we do is we set the time t for 5 seconds. And then we just go into the position equation up here, and we just plug everything in. So when I plug everything into the position equation up there on the very top of the board, I'm going to have, first of all, x naught, which is 0, and then v naught times t, so 50, plus 1/2 a times t squared, so plus 1/2 times negative 2 times 5 squared, and I end up with here a positive number as I should. It ends up being a position of x at 25 meters. So that's how you find the turnaround point, the vertex of the parabola. And lastly, for the remaining 5 seconds of the problem, we go from the origin to negative 37.5 meters. So maybe down here or so, like that. Let's say maybe negative 37.5 meters. So my position goes from here to here. Once again, however, what type of a graph connects the 2 points? And it's a parabola. We have a quadratic term. In this case, which way does the parabola open? In this case, it's upwards because the quadratic term, the acceleration, is a positive number. Now look at this portion of this graph right here. When I do a parabola from here to here, am I going to get to another vertex? No. It's going to look like this. It's a piece of a parabola, kind of roughly like so. Once again, I know this because of the derivative on a position versus time graph, slope of the tangent line, the velocity. So right here at 10 seconds, the slope of the ruler's edge here is negative 10 meters per second. And then the slope goes from negative 10. All right, so as we've seen over the last period or so, the one-dimensional kinematics equations for constant acceleration are perfectly capable of describing what happens when police cars overtake speeders, or when kids walk back and forth in front of desks, and so on and so forth. Walk back and forth in front of desks and so on. But frankly, that's all fine and good, but it really doesn't tell us all that much about nature. And that's what physics is concerned with, is coming up with concise descriptions of nature. So then therefore, why are they so important? Now we once again get back to Galileo. So recall the following from a couple of class periods ago. Recall that according to the ancient Greeks, that heavier objects fall faster than lighter objects. And remember very simply that the ancient Greeks based their conclusions upon simple observations. Okay, recall this very simple demonstration. We've got a light object, a piece of paper, a heavy object, a chunk of iron. And just hold them here above the floor at the same height, let go of them at the same time. Heavier object hits the ground first. Then remember in this simple demonstration that if you do a simple experiment, which the ancient Greeks never did, by just crumpling up the piece of paper like so, and now when you take the two objects here, hold them at the same height above the floor, let go of them at the same time, now they appear to hit the ground at the same time. So a simple demo such as this begins to show that there is once again something wrong with that statement. And now we do in fact get to Galileo Galilei. Well, I've had lots of practice.
Every single time you send that.
Now we're once again in the early 17th century. Galileo was literally the first person to make the following realization, something that everybody here in this room just takes for granted. So for example, before I crumpled up the piece of paper, what was preventing it from falling quickly to the floor?
Air resistance?
Yeah, air resistance. Everybody here in this room knows that. It turns out, however, that Galileo was literally the first person to make this realization, as strange as that may sound. So Galileo realized this. That air resistance slows down falling objects. Everybody here in this room knows this, of course, but he was the first person to realize it. He then, however, goes one step further, though. He asks the following question. What would happen to a falling object, a object, in the absence of air resistance? In other words, by asking this question, Galileo is conceiving of the idea of a vacuum. A vacuum is a region of space where there is no air, no atmosphere. Now today, that's a very easy concept to grasp. For example, if you go to the moon and you stand on the airless surface of the moon, there's no atmosphere there. You're standing in the vacuum. This is an easy idea for us to grasp today. However, 400 years ago, that was a very slippery idea for people to wrap their heads around. Galileo was the first to conceive of the idea of a vacuum. So he's basically asking the question, what would happen to a falling object in a vacuum? And now in order to answer this question, he designs and carries out a very simple experiment. He then bases his conclusions upon the results of his experiment. Now obviously, Galileo is a very important figure in the history of science. In addition to everything else that he's done that I've described thus far, he's also credited with being one of the first people in history to actually do comprehensive experiments and then draw conclusions based upon his experiments and results. So he's a key figure in the development of the scientific method as a process, in addition to doing everything else that he did. Now let me describe to you his very simple experiment. I'm then going to show you a couple of different versions of it, including a more modern example. Now Galileo could not produce a vacuum in a simple, primitive laboratory, but he could envision one, and what he tried to do is he tried to mimic one over short distances. What he did was he took an inclined plane, and he basically made it as smooth as he possibly could. By making the inclined plane very smooth, what he's trying to do is mimic a frictionless surface. As we'll see a little bit later on, there's no such thing as a frictionless surface, and he tried to approximate one as best he could over a very short distance. So he's trying to mimic a frictionless surface. Okay, then he just simply takes an object, sets it onto the incline, and then he releases the object from rest. And then using the kinematics equations for one-dimensional motion with constant acceleration, he was, by the way, one of the first people in history to derive the equations. He then uses the equations to measure the acceleration. So as the object slides down the slope here, it has an acceleration A. So he measured the acceleration. And now here was his experimental result. The result was, regardless of the weight of the object, the acceleration was always the same value. Regardless of the weight of the object, the acceleration was the same value. In other words, he just basically did the following. Here's a very simple version of this. Let me use my eraser here. The eraser here is quite light, it only weighs a couple of ounces. And then here's a nice smooth inclined plane. And then what he did is he just took the eraser, for example, set it onto the incline, let it go, and accelerates from rest. He then measured the acceleration. And then he did the same thing with a heavy chunk of iron, for example. Set it onto the incline, let it go, it accelerates from rest. And he found that the acceleration of this object was exactly the same as the acceleration of this object. And then what he did was he took the inclined plane and he tilted it at a steeper angle. And he then repeated the experiment. So you take this guy here and measure its acceleration like so. Take this guy here and measure its acceleration like so, and find that it was exactly the same value. It was a greater value than when the plane was like so at a shallower angle, but the result was the same in the following sense. Regardless of the weight of the object, the acceleration was the same. Therefore, you can conclude the following. Imagine taking the inclined plane and now tilting it so it's vertical. There's no friction. In other words, there's no air resistance. So then therefore, what can you conclude about the acceleration of these two objects in the absence of air resistance? That they fall with the same constant acceleration. And that's the conclusion that you immediately draw from this experimental result. All objects, regardless of weight, fall with the same constant acceleration. In the absence of air resistance. So by arriving at this experimental result, here in blue, realizing what it means, this conclusion, all objects regardless of weight follow the same constant acceleration in the absence of air resistance. Now that we have this experimentally confirmed result, what can we say about this statement regarding motion according to the ancient Greeks? Yeah, it's obviously incorrect. Okay, what Galileo discovered, by the way, is referred to as free fall. An object in free fall falls with the same constant acceleration, regardless of weight, in the absence of air resistance. Object in free fall, as we say, falls with the same constant acceleration, regardless of weight, in the absence of air resistance. That acceleration, by the way, is so important when describing motion near the surface of the Earth that it's given its own symbol. The symbol for this acceleration is the letter small g. It is not referred to as gravity. It is referred to as acceleration due to gravity. The value of g was first measured in his experiments by Galileo more than 400 years ago. It's a number you've already seen in class in one of my examples from last class period. In metric SI units, the acceleration due to gravity is equal to 9.8 meters per second squared. However, if you're using the old imperial or English units system, it's equal to 32 feet per second squared. You know, as I said earlier, I can show you a more modern version here of Galileo's experiment. He could not do the following 400 years ago, but I actually can do this here in my room today. He couldn't produce a vacuum in his own primitive laboratory, but it turns out that I could actually produce a pretty good vacuum here inside this classroom by means of that vacuum apparatus. Okay, right here in this tube, there are two objects. There's a penny and a feather. And right now, because the tube is open here, there's a lot of air inside the tube. And we can see that very easily because there's a lot of air resistance. For example, it acts upon the feather when I do this, like so. So this is like the paper in the chunk of iron, obviously, from a few minutes ago. And now what I'm going to do by means of this vacuum pump, and this would have amazed Galileo 400 years ago, is I'm going to remove the air from the tube. So Galileo has to put the hose on it like so. And then he has to plug it into the wall socket. Of course, 400 years ago, he didn't have the wall socket. So, and now I'm going to turn the pump on. And it's starting to remove some of the air from the tube. Now, it doesn't remove all of the air from the tube. It's not going to produce a perfect vacuum. But even after just a few seconds, it actually does, in fact, remove most of the air from the tube. So now watch what happens, for example, if I tip it over. Notice that the acceleration of the penny and the feather are more and more becoming the same thing. Once again, in the absence of air resistance, the acceleration of both of the objects is going to be exactly the same, downwards at 9.8. Make sure that we clear up some misconceptions about an object in free fall that you may have had prior to today's lesson. Okay, so first of all, if I take an object and drop it, this chunk of iron, by the way, there's very little air resistance that acts upon it. It's essentially accelerating due to gravity downwards at 9.8 meters per second squared. It's essentially in free fall. So if I let go of it from rest, it accelerates downwards at 9.8 meters per second squared. If I take the object, however, and I throw it downwards like so, while it's in my hand, it is not in free fall. But the instant that I let go of it, it then is in free fall and accelerates downwards at 9.8 meters per second squared. Notice, however, the speed of the object when I threw it downwards, the instant prior to hitting the ground, was greater than the speed of the object when I dropped it, the instant prior to hitting the ground. Look at it carefully. So if I just drop it from rest, it looks like so. And then secondly, this guy keeps rolling away from me. If I throw it downwards like so, it obviously has a greater speed before it hits the ground here when I throw it, as opposed to dropping it. But in both cases, the acceleration is exactly the same at 9.8 meters per second squared, once it's in free fall. Yeah, that's pretty simple and straightforward. Usually what trips most people up, however, is the following. Let's say I take the object and I initially throw it upwards like so. While it's moving upwards, is it still accelerating downwards at 9.8 meters per second squared? Absolutely. There's nothing different about the Earth's gravity while the object is moving upwards as opposed to moving downwards. It's still the same Earth. So the acceleration of the object while it's moving upwards is still downwards at 9.8 meters per second squared. If you're having trouble wrapping your head around that, just think of it like this. Just look at the velocity vectors. So for an object thrown up, such as the marker, the instant that it leaves my hand, it has an initial velocity vector v0 that, say, looks something like this. But then as it's moving upwards, it's slowing down as it does. So a moment later, it has a velocity vector v that looks like this. Now, using the tail-to-tip method of vector addition, remember that initial plus change is equal to final. So on this simple vector diagram, the delta v vector, the change in velocity vector, that becomes like this. Notice that initial plus change is equal to final. Remember that the direction of the delta v vector from last time in class is the same as the direction as the acceleration vector. So the acceleration vector is downwards at 9.8 meters per second squared. Once again, just think of it very simply like this. There's nothing different about the Earth's gravity. While the object is moving upwards as opposed to downwards, it's still the same Earth. Therefore, acceleration due to gravity is the same value, 9.8 meters per second squared. Now, an object in free fall is undergoing one-dimensional motion with constant acceleration. So then, therefore, the kinematics equations that we've been working with over the last period or so, they apply to this situation as well. But we do rename the equations slightly. Let me just erase them. So now, free fall kinematics. Earlier, of course, in the chapter when dealing with cars and bicycles and people walking back and forth along a horizontal number line, it was just that. It was described in the horizontal direction, which we always thought of as the x-axis. An object in free fall, however, that motion occurs vertically. So instead of using the x-axis to describe everything, we use the y-axis instead. So we basically replace all of the x's that we saw in the previous equations with y's. In addition to that, for an object in free fall, the acceleration is always the same thing, is g downwards at 9.8 meters per second squared. So we then rewrite the kinematics expressions in the following way. Okay, first of all, position. We write the final position not as x, but instead as y. And then we have the initial position, which is written as y0. And then the next term is the initial velocity multiplied by the time. The initial velocity is in the y direction. We write this as vy0. And then we have our plus 1/2 at squared term. Well, the acceleration is downwards at g. And then, as is our standard, we always think of downwards as negative and upwards as positive. So because the acceleration is downwards, we think of that as negative for that reason. And we write the minus 1/2 gt squared term like so, as representing the plus 1/2 at squared that we saw earlier for horizontal cases. Okay, then we have the velocity equation. So we have our final velocity, but now in the y direction, so it's written as v sub y. equals then the initial velocity, Vy naught. And then we have plus AT. So we now write that as minus GT like so, because once again, the acceleration is equal to G, and we think of the downwards direction as the negative direction. If you algebraically combine these equations together, by the way, to get the third kinematics equation, in its free fall form, the third kinematics equation looks like this. Okay, before we begin to look at quantitative examples and then eventually a laboratory exercise, kind of like focusing in on what I did earlier today, let me quickly sketch out what these equations look like. I'm sorry, you actually have a question. No. The magnitude of it is 9.8 meters per second squared, but it is an acceleration, so it's a vector. There's a direction associated. Usually with simple free fall problems, such as what we'll be tackling, we always think of up as positive and down as negative. So because the acceleration is downwards, we make that a negative number, hence the negative sign appearing here in the expressions. It's just a number, 9.8 meters per second squared, but the downwards direction we just think of as negative by definition. As you'll see, it makes things easy to deal with. Okay? Okay, let me sketch out what these equations look like for three simple situations. Once again, this is to clear up misconceptions that you may have had previously. Okay, as I do this, however, let's say the object starts at the origin, so the initial position is equal to 0. Y naught is equal to 0. And I'm just going to quickly sketch out here three situations, three possibilities. The first possibility is the easiest one, for an object dropped from rest. So if the object is dropped from rest, what that means is that the initial velocity, Vy naught, that's the symbol for it, is equal to 0. So when the object is in free fall, if I now graph down its acceleration as a function of time, it's always the same thing. It's 9.8 meters per second squared downwards, which we think of as the negative direction. So here's the constant acceleration downwards and a value of g. It doesn't matter, however, for my later situations, if the object is thrown downwards or if the object is thrown upwards initially. In all cases, the acceleration is the same. Then, we have velocity as a function of time. Okay, like earlier today, when we graph velocity as a function of time, we're graphing a linear equation. The slope of the line, however, is always the same thing. It's just minus g. The only thing that will change from scenario to scenario is Vy naught, that is the y-intercept. So for an object that is dropped from rest, its velocity as a function of time just looks like this. A line like so, with a slope minus g, and the y-intercept here is right at 0 for an object that is dropped from rest. And lastly, its position as a function of time. Okay, like from earlier today, we're graphing a quadratic. So it's a parabola. It's always the same parabola in the sense that it opens downwards. For an object that is dropped from rest, however, the vertex of the parabola is here at the origin. It looks like this. And once again, we know this from the derivative. On a position versus time graph, the slope of the ruler's edge, the tangent line, that's the velocity. So right here at the vertex, notice that the slope of the ruler's edge there is 0. In other words, the object is dropped from rest. And then notice that the slope here just gets increasingly more and more negative as the object falls. In other words, it speeds up in the negative direction. Okay, this situation here is pretty straightforward. Okay, the second situation is also pretty easy. This is for an object thrown downwards. For an object thrown downwards, the only thing that's different is that the initial velocity, Vy naught, is a negative number. In other words, remember that down is negative. With the thrown object downwards, the initial velocity vector is negative. It's pointing in the downwards direction. When the object is in free fall, however, its acceleration is exactly the same as before. It has an acceleration downwards at a value of g. If we were to plot, however, its velocity as a function of time, it's the exact same line as before, that is with a slope of minus g, it's just now that the y-intercept is a negative number. So then therefore it just looks like this. Makes sense? Similarly, if I graph position as a function of time, it's the exact same parabola as before, but in this case the vertex is not at the origin. The vertex is actually back here somewhere. It kind of looks like this. Well, kind of exaggerated here for clarity. So, where this right here is not the vertex. Once again, I know this from the idea of the derivative. So right here at the origin, when we start the clock, for example, notice the slope of the ruler's edge there is a negative number. That's this negative initial velocity. And then the velocity goes from this initial negative number and it just speeds up in the negative direction. Like so, it speeds up in the negative direction. Once again, this is pretty straightforward. What usually trips everybody up, however, is the last situation. And that's where the object was thrown upwards. For the object thrown upwards, the initial velocity is a positive number. Just keep it straight once again, however, keep in mind that even though the marker is moving upwards initially, it's in free fall, his acceleration is still downwards at 9.8 meters per second squared. Same acceleration graph. When I graph out the velocity, it's going to be the exact same line as the other two graphs, but now the y-intercept is a positive number. That then has to look like this. So it's still the same slope of minus g, but right here is now the initial velocity, which is a positive number. So here's what's happening on this graph. The object is initially moving upwards and slowing down as it does, reaches a velocity of 0 when it's at its maximum height, and then it just speeds up in the negative direction like so. And let me ask you this, by the way. If I take the marker and I throw it upwards like so, and it reaches its maximum height, how long is the object at its maximum height before? How long is the marker there at its maximum height? For literally an instant in time, a non-measurable amount of time. Imagine what that last velocity graph would look like, by the way, if the marker was at its maximum height for a measurable amount of time. It would look like this. Don't draw this. So we would have, for example, the marker moving upwards and slowing down as it does, reaches a velocity of 0 when it reaches its maximum height, and then just by itself it decides to stay there for a while like so. And then just by itself decides to fall down in the negative direction like that. So of course this is not what happens. What does happen is that the marker is at its maximum height for an instant in time, literally a non-measurable amount of time, and then moves downwards like so, speeding up as it does. This right here, by the way, this graph right here would describe, for example, the physics of the Warner Brothers cartoon world. You guys ever watch the old Warner Brothers cartoons? Where the Wile E. Coyote chases, for example, the Roadrunner? The Wile E. Coyote goes off the cliff, but he stays there for a moment. He stays there until he notices that he's fallen off the cliff, and then he falls down. So the Wile E. Coyote stays there for a moment until he notices that he's fallen off the cliff, and then he's falling down. That graph right there describes the laws of physics in the Warner Brothers cartoon world. That, of course, is not what really happens. What really happens is the following. Did you guys know, by the way, that another basic law of nature in the Warner Brothers cartoon world is the following? You can walk to a wall as long as there is a tunnel painted on the wall. That's another one of the laws of nature in the Warner Brothers cartoon world. Another one of my favorites from Warner Brothers is a cat will conform to the shape of its container. That's another law of nature in the Warner Brothers cartoon world. Okay, lastly, for these basic graphs. Okay, for the object thrown upwards, position. function type. It's the exact same parabola as before, but in this case, the parabola's vertex is in the first quadrant. Looks like this. So once again, in terms of the derivative, if you initially throw the object upwards, notice the initial velocity is a positive number. That's right here. And then the object reaches its maximum height with a velocity of 0. It's right there. And then we go from the velocity of 0 to a negative value, say down here as the object falls. Here?
The position graphs are relative to like the hand that's throwing it, right?
Not relative to the hand that's throwing it, but relative to an origin. So I'm just going to say here, for the purposes of simplicity, when I do graph these out, these simple sketches, that I'm thinking of my hand as the origin. So, however, when we approach mathematical examples, I'll finish the day today with just one example in just a moment, we do things a little bit differently than the horizontal case. In a horizontal case, we always typically think of the object as starting at the origin, x naught is equal to 0, as we've done over and over, but not so in the vertical case. In the vertical case, we typically think of the ground as the origin. It's a nice point of reference, and then just go from there. So let's finish the day with one simple example. This is about as simple as free fall gets. Okay, so as far as free fall problems go, this is about as easy as it gets. An object is at some height and then is dropped from rest. As I mentioned a few moments ago, we do things a little bit differently with basic freefall problems as opposed to horizontal cases from earlier in the chapter. Typically when dealing with freefall, because it's a nice point of reference, we always think of the ground as the origin. And so then therefore, if the object is dropped from rest up here at a height of 30 meters above the ground, what that means is that the initial position vector y naught, which looks like so, that's equal to 30 meters. And then the object is dropped from rest, so the initial velocity v y naught is equal to 0. Now note the phrasing in the problem as you get down towards the bottom in part B. If you see the phrasing as such, the instant that it strikes the ground or the instant prior to striking the ground, it means the same thing. The reason for that is because an instant is literally a non-measurable amount of time. So in other words, it's basically the last possible moment that the object is in free fall. I mean, after it hits the ground, it's no longer in free fall, so its velocity would be 0, but frankly, we don't care. We want to describe what happens the last possible instant that the object is in free fall. That's when it reaches a position here, y equal to 0, and it does so at a final velocity v sub y in a certain amount of time t that we're trying to find. So once again, don't be confused here by the phrasing. In a problem such as this, it's the last possible instant that the object is in free fall. Afterwards, it's not in free fall, and then therefore we don't care. Okay, now just like you saw me do earlier in the chapter, you always just start by drawing out a diagram. You draw your knowns and unknown quantities, and now we get to our equations and we start plugging in our zeros. Okay, let's take a look at the position equation first. Notice that two things are 0. The final position and the initial velocity. So then therefore, in part A of the problem, if I plug in my zeros here into this expression, I get the following. So take a look at that carefully. The final position is 0, and the initial velocity is 0, so the equation simplifies to this. And then in this expression, what is the only unknown? That's the time t, so I can solve it. So at this point, just a little bit of algebra. So move the 1/2 gt squared to the other side, like so. Okay, then cross multiply by the 2 and the g, and then take the square root of both sides. So after you do those couple of minor mathematical steps, this is what you'll end up with. Like so, and now I just plug in my numbers. When I plug in my numbers, do I plug in for g here, by the way, positive or negative 9.8 meters per second squared? Positive. The negative sign is already taken care of in the equations. You just plug in the magnitudes when you get to this point. All the directions have already been accounted for. So then therefore, it's just a square root of 2 times 30 divided by 9.8. And that works out to be a little bit less than 2.5 seconds. It's about 2.47 seconds. And now that I have that time, the last thing to do is now take a look here in part B of the problem at the velocity equation. So in the velocity equation, plugging in our zeros, keep in mind that the object was dropped from rest. So this term here is equal to 0. So the velocity equation then simplifies to become this. So keep in mind that the minus sign is there from the expression itself. And now we just plug in minus and then just 9.8 times 2.47. Multiply that out, and I end up with about a negative 24.2 meters per second. So the object's final speed is 24.2 meters per second. This is its speed the instant prior to hitting the ground, or the instant it hits the ground. It means the same thing. It's the last possible moment that the object is in free fall. The negative sign means what about the vector itself? That it points downwards. So, okay. Right. I've got something to pass on to you. And unfortunately, your textbook, and also on WebAssign, doesn't do a really good job of providing a nice quantitative example involving graphs like I did, for example, here in class today. So because of that, then I have these two problems here that are to be done by hand. Now there's lots of stuff going on, not just today, obviously, in class, but on Friday as well. On Friday, you're going to be doing your first comprehensive laboratory exercise. There will be a laboratory report associated. We'll get to that, however, a little bit later on. Basically, what you're going to do on Friday is you're going to measure G. It's actually really easy to do. So because of that, and in addition, we have 2 web assignments that are due this week. For this assignment here, I'm going to give you plenty of time to do it, just so you're not bogged down by a lot of stuff. So taking a look here at the agenda board, even though these are only 2 problems, I'm going to collect them from you actually on Tuesday of next week. That's on the 27th. You can, of course, do these problems directly on the handout. That's perfectly fine. They're very similar to the example that I did today in class. So for the remaining 15 minutes here or so of class, you could probably pretty easily get the first problem done. Let's go ahead and start to read it together. Notice the first sentence of the problem. It says that a car is moving at constant velocity at 20 meters per second for 5 seconds. So if it's moving at constant velocity, what does that immediately mean about the acceleration of the car for the first 5 seconds? That is equal to 0. So keep that in mind here as you now start problem number 1. So go ahead and do so. And whose ever phone this is who is recording here?